Hello, this is Mr. White, and this video is on solving trigonometric equations. And if everything is going according to current plan, we've already introduced this topic in class and done some relatively simple equations. And in this video, we're going to do a slightly more complicated one. So we still need to have a solid grasp on all our basic trig identities, all our fundamental trig identities. And we need to recognize the clues that would indicate which one we're going to use at which time. Now, in this example, we're certainly not going to use every single one of these identities, but they are all fair game. So again, you need to be solid on all of them. Okay, let's jump in. This example says, find all the solutions to the trigonometric equation without a calculator. Secant x plus tangent x equals 2 cosine of x. Now, you just kind of step back and study it. I will admit that it's not obvious which trig identity to start out with. And whenever I find that it's not really obvious which one to start with, I often find that that general tip of turning everything into sines and cosines that I gave in the last video, that's often a good way to go if you don't really see any other obvious clues. So let's start with that. Okay, secant of x. To turn that into sine or cosine, we will use our reciprocal identities, and that says that it's 1 over cosine of x. Tangent of x, using our quotient identity, we will write sine of x over cosine of x. And on the right side, it's already in terms of sine and or cosine, so I'll just leave it as 2 cosine of x. And when you do that, when you put everything in terms of sine and cosine, quite often, as we see here, we end up with something kind of fortunate and lucky happen. We look on the left and we say, hey, look at that. It's got the same, both terms have the same denominator. So I could combine those into a single fraction with a common denominator without any extra manipulation. But I think I'm going to do something a little bit more slick here. I'm going to just essentially cancel out that denominator by just multiplying both sides by cosine of x. So again, I could write that as a single fraction, nothing wrong if that's what you choose to do, but I'm going to say let's cancel out that cosine of x. In fact, I'd encourage you to see what happens if you write that as a fraction and whether that would prompt you to do anything differently. All right, so let's see what happens. Just remember that notice that those parentheses that I just put here, especially on the left side, were particularly important because I need to remember to distribute that cosine to both terms. And when I distribute it to the first term, cosine times 1 over cosine is just 1. Cosine times sine over cosine, the cosines effectively cancel each other, and I get sine of x. And on the right-hand side, I've got 2 cosine squared of x. Okay, so we step back a moment and say, okay, what next? Well, let's look at the clues there. Okay, the only clue that I would say is kind of obvious is the cosine squared. Remember, whenever we see a trig function being squared, we should consider whether Pythagorean identities are going to help us out. Now, this is going to sound like I'm contradicting something that I said in the last video, where I indicated that if you were to use the Pythagorean identity, and if it looked like it made the expression more complicated, I indicated that that's often the sign of a wrong turn. So let me go ahead and just do this and show you what I'm talking about. Again, the last video I said that if you replace cosine squared with 1 minus sine squared, that looks like it made it more complicated, right? And I indicated last time that in simplifying expressions that would not be beneficial. But look at it in this case and see that in solving an equation, sometimes it is beneficial. Do you see what that did for us? That took an equation that had 2 different trig functions and it reduced it down to a single trig function of just sine of x. Now yes, there's a sine of x and a sine squared, but at least it's the same trig function. So let's just do a little bit of algebra here. Let's distribute the 2 on the right side. 2 times 1 and then 2 times negative or minus sine squared of x. Again, I commented in the last video that unfortunately I find that as soon as you start throwing trig terms in here, for some reason a lot of students just seem to completely forget all their algebra tricks. And another algebra trick, let's move everything to one side of the equation. Let's take this minus 2 sine squared of x and let's add a 2 sine squared of x to bring it to the other side effectively. And let's subtract this 2 here. And that would give us a 2 sine squared of x plus the sine of x, right, on the left side. Now, you may be wondering why I'm writing it in the order that I am, and there is a reason for that. I'm going to do the plus 1 here, but then the minus 2 from over here will give me a minus 1. And I would hope that at this point you can see how all that came about. Again, I started off with that 2 sine squared of x. So pause if you need to convince yourself that this was the right way to go. And do you see why I wrote it in that order? Well, it has nothing to do with trig identities. It has to do with something that should be near and dear to your heart, quadratic equations. So think back to Algebra 2 and or Algebra 1. And we've got 2 something squared plus that something just to the first power, and then minus a constant. That's a quadratic. And so all those quadratic tricks you've learned in the past still apply. Our first resort for solving a quadratic equation, at least in my book, has always been to try factoring. Now, it doesn't always work, but when it does, it's fairly quick. And I'll just go ahead and tell you that here, when we're dealing with trig equations, I'm going to tell you that 90-something% of the time it will work. So 2 sine squared of x, there's really only one way that that can break up in a quadratic form, and that is to have 2 sine of x in one of these parenthesis sets, and then just a single sine of x in the other one. So if you were to imagine starting to FOIL this out, 2 sine x times sine x would give me my 2 sine squared of x. All right, I see that this minus 1 over here, there's not too many ways that can play out. Whoops. There's going to be a 1 here and a 1 here, and now I just have to figure out the pluses or the minuses. And with a little bit of finagling, I know that there's got to be 1 plus and 1 minus. I'll say plus here and minus here, and just do a little check. Let's just make sure that worked. 2 sine x times sine x, that gave us the 2 sine squared of x. 2 sine x plus 1, that would give us plus 2 sine x, but then minus sine x, that does give us the plus sine x that we desired. And then the last term in the FOIL, the minus 1 and the plus 1, would give us this last term there. So yes, it all FOILs out correctly. And do you remember what we do at this point in solving a quadratic? Well, if I've got 0 on the right side and it's factored on the left side, that is where we set each side equal, or each factor equal to 0. And as always, if any of this isn't making sense, if you need to brush up a little bit on your Algebra 2 skills, come on by, please. Be glad to help you during office hours. So we're going to get 2 sources of equation or of solutions here. We've got 2 equations here. So let's start with the one on the left. 2 sine x minus 1 equals 0. I'm going to solve that fairly quickly. In general, you want to start by just getting the trig term by itself. So get the sine of x all by itself. And when you look at that, sine of x equals 1/2. We recognize that as one of our special trig ratios. And that occurs at 2 places on the unit circle. That occurs in the first quadrant, and that occurs over here. Again, I'm going a little bit quickly because this should be very familiar ground for us. We know that that gives us this angle. Notice again, x is an angle because we're taking sine of x. So that gives us pi over 6. And that also gives us 5 pi over 6. All right? There's one more point I can make about this, but I think I'm going to move to the other side, and then I'll make that other point at the end. Let's go over to this equation here. And sine of x plus 1 equals 0. Once again, get the trig term by itself. And we once again turn to the unit circle and say, where on the unit circle does sine equal -1? And we should say that's down here. That's that quadrantal angle. All the way around here, that's at x equals 3 pi over 2. Now, I have 3 solutions there, but remember the original problem, if I scroll all the way up, the original problem said all solutions. So not just between 0 and 2 pi, but all solutions. So I need to get all the coterminal angles. So the way I'm going to do that, this should seem familiar, and if you didn't catch it the first time around how this works, when we've seen this before, again, this is something you're going to need to understand why we're doing it and how it works. Oh well, there. Trying to clear myself a little space there. So plus 2 pi n, and that is my final solution. 3 angles on the unit circle plus all their coterminal angles. That is all the values, all the solutions to that equation. So let me at this point make one more point about that example, and that is that the book encourages you, and I often encourage you, that even when you're told to do something without a calculator, to check it with a calculator. That's one of the main reasons I want you to learn how to use it. I'm going to admit right off the bat that sometimes checking is very straightforward on these trig equations. Sometimes it can get a little bit tricky, and we will try to get around some of those problems in class. But as you know, I can't really enter secant directly into the calculator, so for the left side of the equation, I type it in as such. For the right side of the equation, 2 cosine of x, that's a little more straightforward. And when I do that and I use the window settings that are seen up there on the screen, I get a graph that looks like this. So the 3 solutions that we had, at least between 0 and 2 pi, were pi over 6, which if you did calc intersect, you would find that yes, pi over 6 is a valid intersection. 5 pi over 6, that was this one right here. And 3 pi over 2, that was this intersection here. So again, not only was it true on the unit circle, but it's also true on this xy plane where we're drawing the trig curves. Now, as far as all the coterminal angles, if I were able to extend that window, again, right now you see that I have it set from 0 to 2 pi, so that means at least the x-min and x-max. But if I were to extend that window, we'd find that that same shape we see up there on the screen, those same curves, would just keep repeating themselves. These are periodic functions. So they would just keep repeating themselves, and we would see those same solutions repeated every interval of 2 pi. So wherever you see a pi over 6 right here, I guess I should move that up a little bit right here. If you jump over a distance of 2 pi, you'll see another one. And if you were to jump another 2 pi, you'd see another one. Or if you were to jump back 2 pi, you'd see that. So that's the plus 2 pi n. Same thing with this one. We see its coterminals, as well as this one's a little bit harder to see, but we see every distance interval 2 pi, we see solutions. Okay, so that's today's example. Hope you're getting the hang of this. Don't forget your algebra, and there is your exercise to try. Again, all trig identities are fair game. So pause the video at this point and give it a shot. All right, I'm going to trust that you have given this a shot, and let's see if you got these answers right here. This would be your solutions to this equation, and graphically it would check out as well. Come on by if you had any problems.